Welcome back, NEET aspirants. In this fourth part of our learning of fascinating territory of mechanical properties of fluids, we are about to unravel the mysteries behind Venturimeter and the speed of flux. So, get ready to ride the waves of fluid dynamics as we explore the intricate dance between the pressure, velocity, and flow. If you have ever wondered how engineers measures and manipulate fluid speed, grab your curiosity because things are about to get fluidly fantastic. Let's dive into the Venturimeter and discover the secrets of the speed of efflux. The Venturimeter, a remarkable device rooted in Bernoulli's principle, stands as a pivotal role for accurately gauging the flow of the liquids through pipe. Imagine a liquid of density rho gracefully traversing a pipe with a cross-sectional area of capital A. Now, within this pipe, there exists a constricted segment marked as A called as throat. To measure the fluid's journey through this constriction or throat, we employ a clever setup. A manometer tube filled with a dense liquid like mercury, density ρ0, is connected to the pipe, as illustrated in accompanying figure. At the point, we identify P1 as the pressure at the initial point, having capital A as the area of wide opening and small a is the area of throat, and P2 as the pressure at the throat, that is point 2. The corresponding velocities at these 2 points are denoted by V1 and V2. Now, applying the principles of fluid dynamics, we establish the relationship between these variables. As the liquid negotiates the throat region, its velocity increases due to the reduced cross-sectional area. Adhering to the conservation of mass, according to Bernoulli's equation, this rises in the velocity is associated with the decrease in the pressure. Therefore, we can express the relationship between the pressure, densities, and velocities using the equation P1 plus half of rho V1 square is equal to P2 plus half rho V2 square. This equation captures the dynamic equilibrium between the kinetic and potential energy of a fluid as it navigates the Venturimeter. By measuring the pressure difference, we can get insight into the fluid's velocity, offering us a precise means to understand and manage the fluid flow in pipe. The Venturimeter, a testament to the elegance of fluid dynamics and Bernoulli's insight, continuing to play a crucial role in various applications from engineering to industrial purpose. Now coming back to our equation and modifying it as P1 minus P2 is equal to half of rho V2 square minus half of rho V1 square. As we know from the equation of continuity, A V1 is equal to A into V2. From the equation of continuity, we get A V1 is equal to A V2. V2 is equal to capital A upon A into V1. Substituting this into the Bernoulli's equation and simplifying, we get P1 minus P2 is equal to half of rho into bracket capital A upon small a into V1 bracket close raised to 2 minus half of rho into V1 square. Simplifying it further, we get P1 minus P2 is equal to half of rho V1 square into bracket capital A square upon small a square minus 1 bracket close. The volume of a liquid flowing through the pipe per second Q is equal to capital A into V1, and P1 minus P2 is equal to H rho 0 G. Speed of efflux. As shown in figure, a tank of cross-sectional area capital A1 filled to a depth H of the liquid of density rho, there is a hole of cross-sectional area A2 at the bottom and the liquid flows out of the tank through the hole. Note, A2 is very small compared to A1. Let V1 and V2 be the speeds of the liquid at A1 and A2 respectively. As both the cross sections are open to the atmosphere, the pressure therefore equals to atmospheric pressure P0. If the height of the free surface above the hole is h1, the Bernoulli's equation gives P0 plus half of rho V1 square plus rho GH equal to P1 plus half of rho V2 square. By the equation of continuity A1 V1 is equal to A2 V2, we get P0 plus half of rho into bracket A2 upon A1 bracket close raised to 2 into V2 square plus rho GH is equal to P1 plus half of rho V2 square. On simplifying, we get V2 is equal to under root of 2GH upon 1 minus into bracket A2 upon A1 bracket close raised to 2. If A2 is very less than A1, the equation reduces to V2 is equal to under root of 2GH. The speed of efflux is the same as the speed a body that could acquire in falling freely through a height edge. This is known as Torseli's theorem. Now, after going through the Venturimeter and Torseli's theorem, let's solve some examples. A Venturimeter is installed in a horizontal pipeline with a throat diameter of 5 cm and enlarged end diameter of 10 cm. The pipeline carries an incompressible fluid at a steady rate. The height of the mercury column in a manometer connected to the Venturimeter is measured to be 4 cm. The density of mercury is 13.6 grams per centimeter cube, and the density of the fluid in the pipeline is 1 grams per centimeter cube. Asked to find out the rate of flow of the incompressible fluid through the Venturimeter. First, we will list out the data given and convert it into SI unit. The throat diameter small d is 5 cm equals to 0.05 meters. Enlarged end diameter capital D is 10 cm equals to 0.1 meter. Height of the mercury column H is 4 cm, which is equal to 0.04. Now, according to the equation for the manometer, P1 minus P2 is equal to H rho 0 G. Substituting the values of H rho 0 and G, we get P1 minus P2 is equal to 0.05 into 13,600 into 9.8, which is equal to 6,664. From the equation for the Venturimeter is equal to P1 minus P2 is equal to half of rho V1 square into bracket capital A square upon small a square minus 1 bracket close. Since area of a circular cross section is given by pi d square by 4, therefore our above equation turns to be P1 minus P2 is equal to half of rho into V1 square into bracket capital D square upon small d square minus 1 bracket close. 6,664 equal to half 1000 into V1 square into bracket 0.1 square divided by 0.05 square minus 1 bracket close. On simplifying the equation, we get 6,664 is equal to 500 V1 square into bracket 4 minus 1 bracket close. On further simplifying, we get V1 is equal to 2.1 meters per second. Volume of a liquid flowing through the pipe per second is given by Q is equal to area into V1. Therefore, Q is equal to pi into capital T square divided by 4 into 2.1. Substituting the values and simplifying it further, we get Q is equal to 0.0165 meters cube per second. Problem 2. Through an opening of a diameter 1 centimeter at the bottom of the tank, water is flowing out at 20 meters per second. What must be the height in meters of water in the tank? The Torseli's theorem also comes in the equation form, that is V is equal to under root of 2gh, where V is the velocity of a fluid, g is acceleration due to the gravity, and h is the height of the fluid above the hole. Therefore, V is equal to under root of 2g h is equal to V square upon 2g. Substituting the values and simplifying it further, we get h is equal to 20 meters. In our next captivating episode, we will take a plunge into the intricate world of molecular theory of surface tension and surface energy. Get ready for a microscopic journey that unveils the secret governing the liquid behavior at the molecular level. Before I, Avinash, from www.ginit.com, sign off, I did like to extend a heartful request. If you found this exploration as intriguing as we did, show us some love by liking, sharing, and subscribing. Your support fuels our passion to bring you more engaging content. Until next time, stay curious and keep exploring the wonders of science. This is Avinash signing off. See you in the next exciting chapter.